So, did I ask you guys how you're feeling? How's everyone feel today? So, this is an opening question. This isn't our question of the day. This is not our objective. This is just like an opening warm-up question. How much force does it take to stop a 65-gram egg thrown 25 meters per second? 25 meters per second is roughly 50 miles per hour. You know, if you double the meters per second, you get a rough mile per hour. And I figure if professional baseball players can throw 90 miles per hour, you know, we should be able to throw 50 miles per hour, right? Yeah? No? Yeah. Okay. And we have like a 65-gram egg, you know, raw egg here. And basically, the question is like, if you wanted to stop the egg, you know, if the egg was going and you wanted to bring it to a stop, how much force would it take to stop this egg? You could always test to see if an egg is raw or hard-boiled. I don't have any hard-boiled to show you this, but if it's raw, you know how a body in motion tends to stay in motion, yes? So there's like that fluidy, you know, yolk on the inside, yes? So if you get this thing spinning, the inside fluid is still spinning, and if you stop it just for a second, if you just stop the shell just for like an instant, then when you pick your finger up, the fluid will, you know, get it going again because the fluid was still in motion. So let's see if I can get this going. If I just. If it was hard-boiled, if you just stop it just like that, it stops. Because it's solid, you stop the whole shebang thing. So you can try that at home. It's a fun little trick. So these are raw, and hopefully you will not find that out today, but you might. So,
I don't like spinning in the front row sometimes.
So, does anybody want to comment on this questionnaire? Does anyone want to hypothesize or make a statement? How much force does it take to stop a 65-gram egg thrown 25 meters per second?
Like horizontally?
Yeah, like horizontally.
I was thinking, like, you can think about what practical uses the question has in your life, and maybe that'll help figure it out. I was wondering, like, why would we need to know?
You said baseball, right?
Yeah. Okay, so that's a good idea. So now it's going to be.
Like, do you mean, like, catch it? Like, if
How
it's
much
thrown to you and you
force?
catch it?
Or just like to have
How
your
much
hand.
force would it take to down the wall, like, catch it?
Anything. You know, one way or another, you have this egg going through the air, and you want to stop that egg. Can we calculate how much force it would take to stop that egg?
Find how much force it takes.
Is that
How much
Isn't
force?
that how much force it
hits
takes?
the wall?
And then you, and then you see that force. It's like every.
Well, the kinetic energy would be measured in joules. Okay, the kinetic energy would be measured in joules, and we want to know how many newtons it would take to stop. But, you know, along that thinking, that could kind of help you along that thinking. It's a trick question, ladies and gentlemen.
Oh, wow.
Okay.
You don't need to answer E.
Because basically, it all depends on.
The distance.
Yeah. Yeah. Good thinking. Or another way of thinking about it, more tied into today's lesson, is the time. Okay. If you want to stop the egg lickety split, then guess what's going to be the deal with the amount of force required? You're going to need a bigger force. If you want to stop it over a long period of time, very gently slow it down to a stop. So, then what would be the deal with the force? Much less. Okay? So, basically, it all has to do with the time. Whoops, wrong computer. So, this leads us to the egg sheet challenge. Obviously, if you throw an egg against the wall, it stops it. Lickety split. And in that short little tiny amount of time, again, what would be the deal with the amount of force required? Yeah, a bigger force, because you have to stop it right away. It takes, But if you throw it into a sheet, what happens to the amount of time required, to stop it? When the egg hits the sheet, what happens? Does it boom, stop right there? It goes in, yes? The sheet kind of says, oh, let me slow you down. Oh, yeah. Oh, there I got you. Now, I'm exaggerating there, yes? But basically, it slows it down over a longer period of time. So the egg sheet challenge, I'm going to basically take a sheet and hold it with a partner as tight as I possibly can.
Oh, that green one? That's what
Scotty throwing an egg.
on the sheet was. Right?
Yeah. Okay?
Well, I want the egg.
And I challenge anyone who wants to try. I don't think anyone in here has the ability to throw the egg
Oh, I can do it.
and hit the sheet. Now,
Hit the sheet? No, it says crack the egg.
crack the egg on the sheet. Have the egg hit the sheet and crack. Now, here's the thing. If you hit the person's hand or near the person's hand, of course, then guess what happens to the amount of time the egg, it's pretty quick. Okay? And, so usually that's not a problem, but the goal is to see, can you break the egg by hitting somewhere near the middle of the sheet. Now, I used to do this in the classroom, but believe it or not, even from close proximity, sometimes people miss the sheet. And then the wall stops the egg rather quickly. So what we do is we go outside down here, and if you don't want to go outside, the hallways have the windows, so everyone can watch from the window. Or if you want to come outside, I don't know what kind of weather we have outside, feel free to come out and try.
Can I please throw the egg?
Okay.
Do we have a diamond?
I swear I have such an
Yeah, but remember, you just block the egg. It's going to rebound and come wrong.
Oh, true.
Wait, this is the game. Williamson.
All right. So. I have 2 eggs for each class, so we're good to go. So, physics explanation of egg demo results. I'm good. Okay. So, describe the motion of an object that has no force acting on it. If you have an object, and you don't have to write this down, this is kind of like, bringing us up to the right thinking. If you have an object that has no force acting on it, what could you say about the motion of that object? Anyone want to comment yet? Adam? Exactly. It's either not moving or it's moving with a constant speed. All right. Describe, still or moving uniformly. Excellent. That's pretty good too, because everyone's tendency is to go back to saying that it's still. And you remember, it could be moving uniformly, which is a little bit counterintuitive. Just law number 2. Describe the motion of an object with a net force acting on it. Go back to Stephen. Yeah, it's accelerating. It's either speeding up, slowing down, or changing direction. State the formula showing the relationship between the force and the acceleration. What was that formula? Okay. Yep. F net equals ma. F equals ma. You know, should be F net. F equals ma. Exactly. All right. So a little chalk and talk.
Chalk and chalk, huh? Chalk and chalk.
You know what? We're going to.
You can say anything. This is today.
Mimeo. Mimeo and talk. Yeah. So we're live. So basically, we know that net force equals mass times acceleration, and basically we learned from our first unit that acceleration is how fast the velocity changes. It's the rate at which velocity changes, so it's the change in velocity over time. So we could just substitute that in to our second law. This basically just says, hey, look, you have a bigger acceleration, you're going to have a bigger force acting on it. If it's a small acceleration, it's going to be a small force. Direct relationship between the acceleration and the force. And then over here we have, acceleration is how fast the velocity changes. So we're just going to substitute that in here, and what do we have? The net force equals the mass times the change in velocity.
So you have a longer time, smaller force.
Exactly. Exactly.
Now,
that is funny. Exactly. Oh. I can't think of any more. Okay. Okay, so here's the thing. Regardless of whether the egg hits the sheet or if the egg hits the teacher in the shoulder, basically the egg had its same initial velocity either way, and the final velocity is going to be what either way? Zero. One way or another, it's going to be brought to a stop, yes? So basically, whether it hits the sheet and gently stops, or whether it hits a brick wall and stops immediately, let me just finish this thought. Either way, we could say that the change in velocity is going to be the same, right? For either case. Exactly. So the mass of the egg is what it is. The egg's going to go through the same change in velocity either way. So what's a big factor that has all the difference, whether it's going to be a big enough force to break the egg or not a big enough force to break the egg? What's the big factor? Time. It's really the only factor, exactly. So basically, if you stop it over a longer period of time, what's going to happen to the required force? It's going to be less. It's going to be smaller. Okay, we'll take a break and then we'll come back and we'll talk more about this. Okay, question, comment?
Yeah. So if Vf is always going to be 0, then you're going to have negative Vi. So is your force going to be negative always? But isn't it not negative force?
It is a negative force because, the egg is going this way, and which way is the force acting on the egg?
This is for stopping it.
This is the force stopping it, yeah. So it is a negative force, so very insightful. It's a negative acceleration because the egg is slowing down. It's a negative acceleration, yes? And therefore, negative force. Very insightful.
Thank you.
Okay.
I think that was Sammy's question.
So, basically, it's kind of like common sense. So let's just get that straight first. And then, of course, you can see with the formula. Common sense says if you're riding down a highway and you realize you don't have any brakes, and on the right side of the road, there's this tremendously long, loose, fluffy hay pile. And on the left side of the road, there's a brick wall. Okay?
Well, if you put it like that.
Which one, would you prefer stopping you? The loose, fluffy hay. And will the loose, fluffy hay stop you lickety-split? No, it'll gently, slowly bring you to a stop over a long period of time. And there'll be much, much less force acting on you. If you decide you want to take the car into the cement wall, you'll be stopped lickety-split. But to stop a car lickety-split takes a tremendous amount of force. So the bigger the amount of time it takes to stop the object, the smaller the amount of force. And you can see that from this relationship right here. Either way, the object's going to go through the same change in velocity. Either way, the object has the same mass. So, basically, if you have a large impact time, then it's going to require a smaller force. So, basically, important fact, the bigger the impact time, the smaller the impact force. Yes? It actually takes more force to bounce it back in some cases, because it takes so much force to stop it, and then if it bounces back, it's going to take so much force to spring it back in the other direction. Yeah. But even that egg did get sprung back a little bit with the sheet. It did spring back, and then we did catch it. But even with that additional spring back force, it still wasn't enough to break the egg. So, yeah. Let's not go back to that. Okay. So there's many examples of this. I think back to my college quad mate. His name was Carl, and he played baseball. He's a really good baseball player. And one day, he just had a catch. I normally never played baseball with him, but we just had a catch, and he was throwing it really hard. Now, of course, if I just kept my glove just right there, even with the glove, if it hit the glove, it stung my hand. So what does the catcher do to kind of not make it hurt as much? You bring it in. So when the ball makes contact, you don't just stop it like that. That's like, ouch! Tiny time, huge force. Right? You catch it, but you bring it back. And people just naturally do that. When you catch it, you just, you bring it back. And even if you're doing the egg toss game, where you're doing the egg toss back and forth, you don't want to just hold your hands just solid. What do you do when you catch the egg? You catch it and you cradle and you bring it back. And what does that giving you? What is that buying you? What is that doing by with that? It gives you more time to slow it down. So you're slowing it down, and bring it to a stop. Athletic shoes. All right. You ask somebody, oh, what do they do for you? Oh, some people say, oh, they have like cushion. They give you that extra cushion, that extra springiness. You know what the bottom line is, ladies and gentlemen? They give you a longer impact time. When you have cushiony shoes, when you go and you run and you land on that shoe, you have a little bit of a downward motion, yes? But if you have a cushioned shoe, you don't stop immediately, but the cushion slows down your downward movement over a longer period of time, much more gently, as opposed to if you have like hard heeled shoes or something, then it's like that's it. You just stop. Airbags. If you're going to be stopped, you'd rather be stopped by the airbag than the steering wheel or the dashboard. Because the steering wheel and the dashboard will stop you lickety split, tremendous amount of force on the body. But when you are stopped by the airbag, it might seem like such a small difference in time, but that tiny bit more time that the airbag takes to slow you down gives you a tremendous decrease in the force. It's amazing, those airbags, because think about it. They have to respond and become fully inflated before you move into them. And so quick. And basically, it's like an explosion. And as soon as the car goes through so much of a deceleration, it triggers the explosion and it explodes that thing right out there. And then there's holes right at the bottom of the airbags, so that after it immediately explodes right out, as you go into it, what do you do to the air? You just push it right on out. But people sometimes get burns from it because that hot air explosion comes out. Has anyone here ever had experience with the airbag?
Well, no, it's like my mom. I was in the back seat, so it releases the gas. That makes it
So it went off on your mom?
Yeah, it smelled like fire. It smelled like fire. It was just like the chemicals that make it hot.
Was she okay?
Yeah.
Oh,
Scary.
Yeah.
That's so scary.
It happened to my dad, and it pushed his watch onto his hand, and it hurt his hand. The watch.
Really?
Yeah.
And one of the reasons why children can't sit up front, it's too much force on them, and it might hurt them, or it could
in the blind side, when he
Stops with his arm.
yeah. So then it's just
so fast reaction. Yeah, that's true.
My dad was in a car crash and they said he airbag take his leg. But he broke his collarbone because of it.
Oh wow. All right. So just to emphasize this again, what does the impact force do when the impact time increases? What does the impact force do when the impact time increases? And Robbie? It decreases. Why do running sneakers prevent knee injuries? Because they increase the time. Okay. So now, basically, folks, we're going to go over the same exact concept with a new language, with new vocabulary. We cover the concept. you increase the time, you decrease the force. But now we're going to explain the same thing with these new words, momentum and impulse. Okay? So this is actually the objective of the lesson here. This is the question. What is the relationship between momentum and impulse? And we're going to address that same egg problem using these new words. I think everyone should have to carry around that thing for a week.
I completely disagree. Couldn't disagree more.
So they have to take it out.
Because, it's a big deal. What is the relationship between momentum and impulse? All right, here we go. Chalk and talk. Mimeo and talk. You've heard that term momentum, like if a athletic team is doing well, they want to keep the momentum going. Or basically anytime something is moving, you want to keep the momentum going. You want to keep it continuing to move. Momentum, what it boils down to, it's an indication of how hard it is to stop an object. If an object has more momentum, it's harder to stop that object. Obviously, if the object isn't moving, it's not that difficult to stop it because it's not moving. So, it doesn't have any momentum. If an object is moving fast, it's pretty hard to stop it. So obviously, momentum is directly proportional to velocity. The faster it goes, the more momentum it has. But there is one other factor as well. Think of the other factor that might affect how difficult it is. Let's say, for example, Jake, the mass. I was going to say, let's say you had a tractor trailer fully loaded with Wii players.
What?
Those.
The Wii.
Oh.
Yeah. And right next to it, you had a Volkswagen Beetlebug, and they're both doing 55 miles per hour going down the LIE. Well, even though they're both going with the same speed, it would be much, much more difficult to stop that tractor trailer. Okay. Oh, okay.
What?
Not for her. So it turns out that momentum has two factors: the mass of the object and the velocity of the object. And if you want to calculate momentum, what it boils down to is momentum equals mass times velocity.
Does it kill
kilogram meters per second, and it's instantaneous velocity. It's the velocity at that particular instant. So whatever its velocity is at that particular instant times its mass, that gives you the object's momentum at that particular instant. Now, a lot of times physicists don't like to write out the formulas with the whole words, so you like to use symbols to make it easier. So, of course, the symbol for mass is m, the symbol for velocity is v. I have no idea why. You get used to it very quickly. But the symbol for momentum is a lowercase p.
What can't be M?
Now you have to be careful because a capital P is pressure as well. I didn't even think about that. Force over area. And a capital P is also power, which is work over time. But in this case,
I have a question.
we have a lowercase p. Yes.
Intensity. What is the symbol?
Rho is a Greek symbol. Rho.
So you drive.
Yeah, what's this row? Called row.
Same.
Almost looks like an italic P.
Yeah, no, letters ago.
And the units are basically what you see is what you get. Kilograms times meters per second. There's no new unit for momentum. It's just kilogram meters per second. Difficult to stop them and you just plow right into it. That's cool. It's very cool. I should get a clip of a hockey scene where the announcer says something, oh, there's too much momentum. That would be cool to have right here. I'm glad you brought that up. That's exactly where we're going. That's exactly where we're going. The momentum is equal to force times the time. And that's exactly where we're heading. So, the last thing I want to say about momentum, it is a vector quantity. You could just write momentum is a vector quantity as direction. A shortcut way of indicating if something's a vector quantity, you could just put an arrow over the quantity. By putting an arrow over it, that indicates, oh, it's a vector quantity. And really cool physicists, instead of putting a whole arrow like that, they leave off the tiny little bottom thing, so you could just put a little thing like this.
I'm going to be a cool physicist to do it.
You know, that just means these are vector quantities. They have direction. And whatever the direction of the velocity, that's the direction of the momentum. If the object is going north, the momentum is north. This leads us to the other new term, which is impulse. Now again, outside of physics, impulse has many different meanings. Like perhaps you have an impulse to throw an egg at your teacher. You know, that's different. Okay.
It's going to be like an ongoing joke throughout the year.
This one here, impulse, is kind of like a force, but there's more information. So if I put an impulse here, on that, I can say, oh, I just put a force on him, or another way of describing, I just put an impulse on him. So impulse is kind of like force, but with impulse there's more information. With impulse, not only do you know how hard the person pushed, but you also know how much time the person was pushing. Because if you push something with a force of 5 newtons for 1 second, and then you push it with 5 newtons for 2 seconds, has a big difference. So how long you're actually pushing it basically is a big factor. So impulse is a push or pull on an object for a certain amount of time. And once again, if you want to calculate impulse, on object
For a certain amount of time.
for an object
For. It was your impulse to write.
yes. Thank you. Impulse equals force times time. Question, Adam?
Cool. What did we say before that? Like force times time equals momentum.
No, before we just said momentum equals mass times velocity, and now we're saying impulse equals force times time, and in a moment we're going to see the relationship between the two.
No, like what did mass say before?
Force times time equals momentum.
Yes. Impulse equals momentum.
Close, actually, close. There is a tiny technical difference, but close. Once again, the symbols, the symbol for force, F, the symbol for time, T, but again, a little bit of a strange symbol for impulse, capital J. Capital J is joules, so you have to be careful. If you have a number with a capital J after it,
Joules.
the J stands for joules. But if you have a formula that has the J in it, the capital J is for impulse.
Is impulse not have a unit?
Impulse does not have its own unique unit. It's just what you see is what you get.
It would be like
Newton seconds.
Think of it as your impulse DJ joules, but it's not.
Exactly.
So it's kilograms per meter.
And once again, force is a vector quantity, and impulse is a vector quantity. And whatever the direction of the force, that's the direction of the impulse. Now this leads us back to today's question: what is the relationship between impulse and momentum? They're close to equal. We just have to be slightly careful here. We know that the overall net force equals mass times acceleration. And we know that we can substitute in the value for acceleration, change in velocity over time. And now I'm just going to kind of like rearrange things a little bit. I'm just going to kind of tweak things. If I multiply both sides by time, I get net force equals mass times change in velocity. And then recall, anytime you have a change in something like change in velocity, it's always the final velocity minus the initial velocity. In some cases it's 0. With the A case it was definitely 0. In other cases it might not be 0, so we're just going to write the whole thing out. It's going to be m times Bf minus Bi. And then if you distribute the m, the force times the time equals the mass times the final velocity minus the mass times the initial velocity. just want to rewrite that same last line. So this is just Newton's second law rearranged. But notice this nicely brings in the new language, because what is force times time? Whoa. What is force times time? That's the impulse put on an object. That's how much was, on the object. In the egg's case, it's going to be a negative impulse because it's slowing the egg down. And what's the mass times the final velocity? It is a momentum. Mass times velocity, that's the definition of momentum. Mass times velocity. But since it's the final velocity, guess which momentum it is? The final momentum. Minus, and the mass times the initial velocity, that's the initial momentum. And final momentum minus initial momentum, basically what's that? No, careful. Change in momentum. So this is the hidden relationship. Impulse doesn't equal the momentum. The impulse equals the change in momentum. Question?
So it only equals the momentum when the final momentum is zero.
True.
That's why.
True. Exactly. Yes.
So is the impulse equal
Mm-hmm. So let me summarize our new batch of equations. We have momentum, it's mass times velocity. Impulse is force times time. And then we have impulse equals change in momentum. Those are the three key formulas. Momentum indicates how hard it is to stop the object. How do you calculate it? Mass times velocity. Impulse, just like a force, but there's more information. You also know how much time the force acted. And impulse also equals change in momentum. Other people like to memorize this third one expanded out. There's many different versions of that third one. For example, that third one can be rewritten: force times time equals mass times final velocity times mass times initial velocity. That's the same formula. This is just the expanded version. Because, what is impulse? Oh, that's force times time. What is the change in momentum? Oh, well, that's the mass times the final velocity minus the mass times the initial velocity. So I think we're ready now to look at a simple problem. So I could have used a hockey problem, but I used a football problem. A football player kicks a .41 kilogram football initially at rest, and the ball flies through the air. If the kicker's foot was in contact with the ball for .051 seconds, and the ball's initial speed after the collision is 21 meters per second, what was the force used?
The collision was the kick.
Yes. You don't have to write down the question. If you want, just write down the data so you can help me when I go through a clear slide. You guys got the data down? You know, I'll help you. You can write down as I write it down. Okay, so what was the mass of the football? And what was its initial velocity? And then it was kicked. And right when it was kicked, how fast was it going? Did anyone get that? 21. So the ball is kicked and leaves the person's foot going 21 meters per second. So this is funny because this would be actually the initial velocity if we were doing a projectile motion problem. Because that's how fast the ball leaves the guy's foot. But in our problem, it's the final velocity. Because the ball was at rest and the person kicks it, pushes it, and right when it leaves contact with the foot, this is how fast it's going. And basically, did they say how much time the foot was in contact with the ball? 0.051 seconds. Okay, so now we want to know how much force did the foot actually put on the ball. Now, to tell you the truth, people, you could have solved this problem before we even did this lesson. Yeah, you could go back to our old language and solve it with force and acceleration. Or you could solve it with the new language, impulse momentum. I'm going to solve it with impulse momentum. I know impulse equals change in momentum. You put an impulse on something, you're going to change the obvious momentum. Impulse is force times time. Change in momentum is mass times final velocity minus mass times initial velocity. And notice we have everything we need now to substitute in. So basically, F times 0.051 seconds equals 0.41 kilograms times 21 meters per second minus 0. No. You can just cross it out. Did anyone print out that force? We rounded to 2 sig figs, 170 newtons. Yeah, that's tricky because it says the ball's initial speed after the collision. But really, that was like the final velocity after the collision. All right. Let's look at some closing questions. What does the impact force do when the impact time increases? So, Olivia? It decreases. Excellent. What is the formula for calculating momentum? Yeah. What is it? Mass times velocity. What are the units for momentum? What you see is what you get, kilograms per second. formula for calculating impulse? Steph? J equals Ft. Impulse equals force times time. What are the units for impulse? Well, Newton seconds. So today's question was, what is the hidden relationship between momentum and impulse? You gotta be careful, you gotta be clear. Amy?
Impulse is equal to the change in momentum.
Yeah, impulse equals the change in momentum. Two identical eggs thrown at the same initial speed. One egg hits a dangling sheet. One egg hits a teacher's shoulder. Back. Which stops the egg more quickly? Less impact time.
The wall or the shoulder?
Exactly. The wall. The wall will stop the egg more quickly.
We tested that before. We did, right? Yeah.
Which egg experiences a greater impact force? Egg that hits the sheet or egg that hits the brick wall? The wall. Egg that hits the brick wall. Okay. Be careful. Be careful. Think about this one for a second. Which egg experiences a greater impulse? Which egg experiences a greater impulse? Olivia? Both experience the same impulse. That's the tricky thing.
Did they both throw on the same force?
No.
Because
one has a lower force, but
They're inversely proportional. So
one has like a big force at small time, and one has a small force at big time.
they're inversely proportional.
But and we know both eggs have the same what? Change in momentum. So if they both have the same change in momentum, they both experience the same impulse. So that's the tricky question.
So we finished lesson 9.
Yeah. Homework day.
Yay.
9.
Can you collect any?
I'm on
No.
I just finished homework 5. I'm on a roll.
Still on. Oh, do you want to bring a dinner away?
If you have your lab notebook, I'll take the lab notebook.
And for conclusion, you just write the hypothesis.
Yeah, I showed
Yes.
Yeah, that's what I remember.
Is this all we were supposed to do? Just the slope, graph, line of estimate, conclusion. Is that all you did?
You wrote the equation of the best fit line?
Elongation, spring constant times force.